At the end of this video, you should be able to identify appropriate coordinate systems for solving problems with vectors, apply the Pythagorean theorem and tangent function to calculate the magnitude and direction of a resultant vector, resolve vectors into components using the sine and cosine functions, and add vectors that are not perpendicular. Chapter 3, Section 2, Vector Operations. Coordinate systems in 2 dimensions. In the chapter Motion in 1 dimension, the motion of a gecko climbing a tree was described as motion along the y-axis. The direction of the displacement of the gecko was denoted by a positive or negative sign. The displacement of the gecko can now be described by an arrow pointing along the y-axis, as is shown on Figure 2.1. A more versatile system for diagramming the motion of an object, however, employs vectors and the use of both the x and y axes simultaneously. The addition of another axis helps determine motion in 2 dimensions and simplifies analysis of motion in 1 dimension. For example, 2 methods can be used to describe the motion of a jet moving at 300 meters per second to the northeast. In one approach, the coordinate system can be turned so that the plane is depicted as moving along the y-axis, as is shown in Figure 2.2a on the screen now. The jet's motion can also be depicted in a 2-dimensional coordinate system whose axes point north and east, as is shown in Figure 2.2b. One problem with the first method is that the axis must be turned again if the direction of the plane changes. Another problem is that the first method provides no way to deal with a second airplane that is not traveling in the same direction as the first airplane. Thus, axes are often designated using fixed directions. For example, in Figure 2.2b, the positive y-axis points north, and the positive x-axis points east. Similarly, when you analyze the motion of objects thrown into the air, orienting the y-axis parallel to the vertical direction simplifies problem solving. Determining resultant magnitude and direction. Earlier, we found the magnitude and direction of a resultant graphically. However, this approach is time-consuming, and the accuracy of the answer depends on how carefully the diagram is drawn and measured. A simpler method uses the Pythagorean theorem and the tangent function. Use the Pythagorean theorem to find the magnitude of a resultant. Imagine a tourist climbing a pyramid in Egypt. The tourist knows the height and width of the pyramid and would like to know the distance covered in a climb from the bottom to the top of the pyramid. Assume that the tourist climbs directly up the middle of one face. As can be seen in Figure 2.3 on the screen now, the magnitude of the tourist's vertical displacement, delta y, is the height of the pyramid. The magnitude of the horizontal displacement, delta x, equals the distance from one edge of the pyramid to the middle, or half the pyramid's width. Notice that these 2 vectors are perpendicular and form a right triangle with a displacement d. As shown in Figure 2.4a, the Pythagorean theorem states that for any right triangle, the square of the hypotenuse, the side opposite the right angle, equals the sum of the squares of the other 2 sides or legs. In Figure 2.4b, the Pythagorean theorem is applied to find the tourist's displacement. The square of the magnitude of the displacement is equal to the sum of the square of the horizontal displacement and the square of the vertical displacement. In this way, you can find out the magnitude of the displacement, d. Use the tangent function to find the direction of the resultant. In order to completely describe the tourist's displacement, you must also know the direction of the tourist's motion. Because delta x, delta y, and d form a right triangle, as is shown in Figure 2.5b on the screen now, the inverse tangent function can be used to find the angle theta, which denotes the direction of the tourist's displacement. For any right triangle, the tangent of an angle is defined as the ratio of the opposite and adjacent legs with respect to a specific acute angle of the right triangle, as is shown in Figure 2.5a. As is also shown on the screen now, the magnitude of the opposite leg divided by the magnitude of the adjacent leg equals the tangent of the angle. Therefore, the inverse of the tangent function, which is shown on the screen, gives the angle. theta is equal to the inverse tangent opposite divided by adjacent. Resolving vectors into components. In the pyramid example, the horizontal and vertical parts that add up to give the torus actual displacement are called components. The x component is parallel to the x-axis. The y component is parallel to the y-axis. Any vector can be completely described by a set of perpendicular components. In this course, components of vectors are shown as outlined, open arrows. Components have arrowheads to indicate their direction. Components are scalars, numbers, but they are signed numbers. The direction is important to determine their sign in the coordinate system. You can often describe an object's motion more conveniently by breaking a single vector into two components, or resolving the vector. Resolving a vector allows you to analyze the motion in each direction. This point is illustrated by examining a scene on the set of an action movie. In this scene, a plane travels at 95 kilometers per hour at an angle of 20 degrees relative to the ground. Filming the plane from below, a camera team travels in a truck directly beneath the plane at all times, as is shown in figure 2.6 on your screen. To find the velocity that the truck must maintain to stay beneath the plane, we must know the horizontal component of the plane's velocity. Once more, the key to solving the problem is to recognize that a right triangle can be drawn using the plane's velocity and its x and y components. The situation can be then analyzed using trigonometry. The sine and cosine functions are defined in terms of the lengths of the sides of such right triangles. The sine of an angle is the ratio of the leg opposite and the angle to the hypotenuse. In figure 2.7 on the screen now, the leg opposite the 20-degree angle represents the y component, right? V sub y, which describes the vertical speed of the airplane. The hypotenuse, v sub plane, is the resultant vector that describes the airplane's total velocity. The cosine of an angle is the ratio between the leg adjacent to the angle and the hypotenuse. In figure 2.7, the adjacent leg represents the x component, velocity sub x, which describes the airplane's horizontal speed. This x component equals the speed required of the truck to remain beneath the plane. Thus, the truck must maintain a speed of v sub x, which is equal to the cosine of 20 degrees multiplied by 95 kilometers per hour, which is equal to 90 kilometers per hour.
In many areas of physics, the necessary first step in solving a problem is finding the x and y components of a vector. Consider an airplane and its velocity during takeoff. How fast is it traveling with respect to the ground, and how fast is it rising in height above the ground? To find these two velocities, the trigonometric functions sine and cosine are used because the vector representing the plane's velocity is the hypotenuse of a right triangle. In this case, to find the x component of the velocity, the definition of cosine is used. The leg of the right triangle adjacent to the 20-degree angle is the x component of the airplane's velocity, which is its ground speed. Finding the y component requires use of the sine function. The leg of the right triangle opposite the 20-degree angle is the y velocity component, which is how fast the airplane is rising vertically. This example illustrates the general method of finding vector components using trigonometric functions and algebra.
Adding vectors that are not perpendicular. Until this point, the vector addition problems concerned vectors that are perpendicular to one another. However, many objects move in one direction and then turn at an angle before continuing their motion. Suppose that an airplane initially travels 5 kilometers at an angle of 35 degrees to the ground, then climbs at only 10 degrees relative to the ground for 22 kilometers. How can you determine the magnitude and direction for the vector denoting the total displacement of the plane? Because the original displacement vectors do not form a right triangle, you cannot apply the tangent function or the Pythagorean theorem when adding the original two vectors. Determining the magnitude and the direction of the resultant can be achieved by resolving each of the plane's displacement vectors into its x and y components. Then the components along each axis can be added together. As is shown in figure 2.8 on the screen now, these sums will be the two perpendicular components of the resultant d. The resultant's magnitude can then be found by using the Pythagorean theorem, and its direction can be found by using the inverse tangent function.
Any two vectors can be added algebraically by simply finding and then adding their x and y components. Find the x and y components of each, as we have done before. The total vector can be found by adding the components. The total x component will be the sum of the x components. The total y component will be the sum of the y components. The result will be the x component and y component of the resultant vector d. The magnitude of the resultant can be found using the Pythagorean theorem. The direction can be found using the tangent function. Since the tangent of an angle is equal to the opposite over the adjacent sides, you can write this. You can then find the direction of the resultant vector with the arctangent or inverse tangent. We now know the exact magnitude and direction of the sum of our two original vectors.
At this point, you should be able to identify appropriate coordinate systems for solving problems with vectors, apply the Pythagorean theorem and tangent function to calculate the magnitude and direction of resultant vectors, resolve vectors into components using the sine and cosine functions, and add vectors that are not perpendicular.